For titrations, there's a couple things to be aware of. There's different styles of problems. The 4 titrations you should be aware of are these 4. Strong acid, strong base, strong base, strong acid, weak acid, strong base, and weak base, strong acid. Okay? Let's go over the plots first. I think that would be a good beginning. The strong acid, strong base, we're always plotting pH versus volume. Though sometimes you'll see us ask for pOH versus volume, which just flips the graph. For strong acid, strong base, is this going to start low or high? Low. Is there a midpoint? No. Is there an EQ point? Yeah. The EQ point, do we know that pH? Yeah, it's 7. Okay, full neutralization. This region down here is called the strong acid region, and we have the strong base region. Okay, the other one, the strong base, strong acid, its counterpart, if you do pH versus volume, is pretty much the exact opposite. It starts high and goes low, still goes through pH 7. Okay, the weak acid, strong base, we'll just do all of them, pH versus volume. It will look like this. It's a little bit longer of a lead up. We've got a midpoint here. We've got an EQ point right there. The first region here is called buffer region, then it goes to the strong base region. For the weak base, strong acid, it's kind of almost the inverted equivalent of that. It goes like this. We got pH versus volume, the EQ point, we got the midpoint. So we start with the buffer region, then go to the strong acid region. Okay? At the midpoint, so there's several things to know. It depends on what kind of problem it is, what's going to be the most important. For a non-traditional problem, you'll want to know a little bit of information about the midpoint and the equivalence point. So let me put this up. This is page 98 of my reader. Right here, let's go through these to make sure they make sense. You'll want to know all these things about the midpoint and all of these things about the equivalence point, especially if it's non-traditional. Okay. At the midpoint, the volume of the titrants added, the strong one, whatever the strong one is half the volume of to get to the equivalence point. So that's the counterpart down here for the equivalence point. The volume of the strong one, it's halfway, and the volume, oh, here we go. The moles, or the volume of the weak equals the volume of the strong at the EQ point. Let's see, what else? Here at the midpoint, you're only halfway in the number of moles given by the titrant. The other important piece of information, pH equals pKa at the midpoint. The equivalence point, so you'll be able to use the buffer equation here, or really just pH equals pKa. Where down here at the equivalence point, you'll have to use the ice table to solve this one. Okay, so it just depends where you're at. I think I have a couple examples. Maybe, yes, that we could go through just so you can see some different kinds of things. Look on the practice exams to see the different styles, the ways we can ask you different types of questions on this. Let me flip over, find some fun titration problems. Here we go, here's one. Yeah. Okay. We'll try this one together, just so you can kind of get warmed up. Okay, so here just like one representative example here. We've got sodium hydroxide. We're adding this to the acetic acid, so we want to find the pH for this solution. So first we want to figure out what kind of titration we have. We have a weak acid with a strong base. So it's this one. Okay, let's find out how many moles of each we have, and that will tell us how to solve it. So we got the 0 point for the weak acid, which is the acetic acid, 0.1 molar times 50 milliliters, and that's 5 millimoles. Okay, for the strong base, that's the sodium hydroxide. Let's zoom out a little bit. There we go. For the strong base, we're all also 0.10 molar, but 10 milliliters. So this is going to be 1 millimole. So in this case, we're in what region? The buffer region, because the weak acid is in excess. If the weak thing is in excess, that's the buffer region. So you will use the Henderson-Hasselbalch in order to solve this. Okay, so it helps. You don't have to do this part if you can do it in your head. But just in case you can't, let's write this out. Let's write out the weak acid. It's going to react with a strong base. I'm not writing sodium because it's a spectator ion. This will go forward. The weak acid will lose a proton, and the base will gain a proton. This started with 5, and this started with 1. 0, and we ignore water. We're going to subtract the limiting reactant, which is the smaller one, and add that amount to the products. So we get 4, 0, and 1. So you see now why we have a buffer. We have, where my pen is, the conjugate base, and then we have 4 of the original weak acid. So you could use the ice table, but it's much easier to use the Henderson-Hasselbalch at this point. pKa plus the log of base of the acid. The pKa, you're given the Ka in the problem. I'll put that down here. K is given in the problem. I'll write that on the next line. So you do the negative log, 1.8 times 10 to the minus 5, plus the log of the base over the acid. Now, do I need to convert this to molarity? No, because it's a ratio. You could if you want to waste a little time, and that would be the sum of the milliliters. So 50 and 10 or 60, as such. So, but you can see they're going to divide out. Am I expecting to get a pH above or below 7? What's in excess? An acid. It better be below 7. Okay, is it going to be really low, like close to 0, or somewhere in the middle, or close to 7? It's a weak acid. I expect it somewhere in the middle. Okay, not too low, probably not too close to 7. I got 4.14. Which makes sense. This, though we didn't calculate this explicitly, this is 4.74. You're expecting a pH within 1 pH unit of the pKa. Okay, now let's make this problem, which it's not very fun right now, a little more fun. Okay? So let's change pen colors. Okay? First of all, I want to know the pH at the midpoint. How do I find that? It's just pKa. So that's 4.74. Okay? I want to know the, what else would we want to know at the midpoint? How about the volume of the strong base added? And how about the millimoles of the strong base? Both at the midpoint. So at the midpoint, both of these. Okay, let's tackle those. Let's rewind a little bit. How much of the weak acid do I have? 50 milliliters, 0.1 molar, so a total of 5 millimoles. Okay? So how many millimoles of the strong base am I expecting at the midpoint? How many millimoles? 2.5. There we go. Okay, I heard people mumbling. I wasn't sure what it was. So, if the weak acid is 5 millimoles, then at the midpoint, the strong base is 2.5 millimoles, or halfway there. Okay? So, let's say we had the strong base. It was 0.10 molar. So 0.10 molar times what volume is going to get me to 25 or 2.5 millimoles? Oh, I said it. Shoot. Okay, never mind. 25 times 0.1 will get you to 2.5. So the millimoles of strong base is going to be 2.5 at the midpoint, and the volume of the strong base will be 25 milliliters at the midpoint. This is a way to kind of, for us to twist the problem around a little bit for you so you have a little more fun on the final. Okay, let's talk about the EQ point for a little bit. Okay, I want to know, again, the millimoles of strong base at the equivalence point, and I want to know the volume of the strong base at the equivalence point. So let's try those. Okay, first the millimoles of strong base. What would that be? 5. For the strong base, it's 2.5 was halfway there. When the millimoles of strong base equal the millimoles of weak acid originally, then we're at the equivalence point. Okay, to find the volume, you just say, well, I have 0.10 molar. I'm going to multiply by some amount of milliliters, and I'll get to 5 millimoles. That sounds like 50 milliliters would be the volume. So here's the volume at the midpoint, or sorry, equivalence point, and here's the millimoles at the equivalence point. So you want to be able to work with the equivalence point and the midpoint in that sort of way. Be able to mess around. Okay, now, just for fun, I don't think we'll do this calculation. How would I find the pH at the EQ point? First, what method would I use? You'll have to use the ice table. Am I expecting the pH compared to 7 to be larger or smaller? Larger than 7, because you're going to run out of the weak acid and all that's left is the conjugate weak base. Okay? So expecting your final answer to be somewhere larger than 7. 8, maybe 9, depends on the concentration. Okay? So make sure you can do these sorts of things for the exam. Okay, any questions on titrations before I move on? I did the plots and midpoint, EQ point. I think that's kind of a sweeping view of it. This I would expect, if I were me and writing the test, to be a long answer question. What else could it be? It's awesome. It involves almost every concept of the course. Okay. All right, moving on. Let's talk about G, delta G here. We'll do, with delta G, we'll also do spontaneity. So I'll do the G and spontaneity all together. I don't remember if I have. Okay. Let's do a summary first, and I'll see if I have an example question or not. I'm not sure at the moment. Okay. Delta G has 2 classic formulas you want to be able to use. This, and of course there can be the version with standard states. If we give you values, they're probably the standard state values. And then, so those two go together. And then there's the delta G, is delta G standard plus RT ln Q. And the equivalent at equilibrium, delta G standard, is minus RT ln K. Okay, let's do a little mini Q&A here. Okay, Q or K, which one is a constant for a given reaction? K, doesn't change. Something like the temperature would need to change for K to change. Otherwise, it's a constant, literally called the equilibrium constant. Okay. I'll put my pens, I guess, like this. Top one or bottom one, if any, which one is a constant for a given reaction? Bottom, the standard. So the standard one. So everything that says standard next to it is a constant for that given reaction, unless something major changes, like the temperature. Okay, let me make it trickier then. Let's say I have that one right there, that delta G standard. What if I change the concentrations or partial pressures? Does that delta G standard change? No, it doesn't change. And again, it's a constant, just like K is a constant. If you change the, you're not changing K or delta G standard or any of the standards if you move around the concentrations or partial pressures or things like that. Okay. Now, how do you find delta G standard? One way to find, so for delta G standard, I'm doing black pen here. So you can find it with that equation if you have K, this equation if you have delta H and delta S standard, or if you don't have either of those, you've got the delta G of formation values, is another way, products minus reactants. Or, similar, analogous to that, if you have the delta H of formation values and the molar entropy standard values, then you can use this. Let's go to a different pen color. This will get you to delta H standard. This will get you to delta S standard. And then you can use the equation right where my pen is here to get to delta G standard. Okay? So there's a couple different ways that you can get to delta G standard. All right, let me see. I don't remember if I had an example question on this or not. Just flipping around here. Oh, did I do this one in class? I did do that. Did I do this one in class? Wow, people don't know. It would have been this class. I forgot too. Totally blanked out. Okay, if we don't know, maybe I should do a little bit of it. Okay. So here, if you want to find KEQ, am I going to use delta G non-standard to solve this? Well, I use delta G non-standard to solve this. No. Because there's no pressures, there's no partial pressures, there's no concentrations, anything like that. All right, first of all, notice we don't give you all the delta H standard values, so these would be 0, because they're for elemental form. We know that we can find K only, given thermodynamic data, only from this. So we can get to K if we can get to delta G standard. Remember, we can get to delta G standard if we have delta G of formation values, which we don't, or also if we have delta H of formation and molar entropy values, which we do. So we're going to use this method right here. I'll just kind of do, you can do the math at home, I'll just do the overall. You're going to go delta H standard is the delta H of formation of the products, all the products, minus the delta H of formation of all the reactants. And then the delta S standard is the molar entropy of the products, minus the molar entropy of the reactants. Okay, I'll let you do all that math and fun stuff at home. That would be good practice. For the delta S standard, down here, I got minus 543 joules per mole. And for the delta H standard, I got negative 1652. Oh, I put kilojoules per mole, sorry, joules per Kelvin down there. All right. And then it's using the other equation for delta G that we had up before, which is this. Delta G standard is equal to delta H standard minus T delta S. Okay, again, I'll let you calculate that. I'll tell you what I got. I got negative 1.49 times 10 to the 6th joules. A couple things. Make sure you've got the same units. It's not the same right now. So joules or both kilojoules, whatever you prefer, or whatever the problem asks for, and then make sure the temperature is in Kelvin. Is this spontaneous? Yeah, that's spontaneous. So am I expecting a K larger or smaller than 1? Larger. If it's spontaneous, for the constant, I'm expecting also the K to be larger than 1 to make the products favored. Make sure you can manipulate this equation. Again, I'll let you have the fun of doing that. You're going to put in delta G here, RT, solve for K. For K, I got a very large number, 10 to the 261st power. So the right-hand side, or the products, is favored. Okay. So make sure you can tell which side is favored, what side is spontaneous, or really is the reaction spontaneous or non-spontaneous. Make sure you can use all those equations that I wrote up earlier. All these. If you are given, so I want to say something about this equation. If you are given partial pressures or concentrations, you are most likely going to use that equation where my pen is at right now. Partial pressures or concentrations, you're probably going to use that one. And you'll probably ask for a non-standard delta G. So read the problem really carefully. You basically need to see, is there a 0 in the question, or not this superscript 0? All right. That's that. Anything I missed with delta G or spontaneity that you're curious about before we go on to all these K problems here? Oh, all the equations that I wrote for delta G, yeah, they're provided, I believe, on the final. If you're my class, you saw what I showed you the equation page already of the final at the last class. I think they were all there. Shouldn't have to memorize those.